So the next speaker is Michele Nottoli. Thank you, and go ahead.
So, thanks for the introduction, and thanks for organizing. This session was really great with all these ideas about Poisson-Boltzmann solvers. And I will bring some information about yet another Poisson-Boltzmann solver that we have developed as a collaboration between chemists and mathematicians, which is collected in this domain decomposition library for continuum solvation models. The introduction, well, we know it already. We have condensed phase, which is challenging, and most of the processes we are interested about happen in condensed phase. And for this reason, cropping the system is not really accurate. So what is really convenient is to still there? Okay. So cropping is not accurate, but it's a better idea is to use different models for different parts. We usually use a more accurate model for what we are interested in and something more approximate for the rest. And in particular, if the environment is quite homogeneous and we have an interesting solute in it, we can go to a continuum description where we use some simple parameters to describe the solvent, and everything becomes a classical electrostatic problem. The main ingredients that we have already seen somehow this morning are the cavity. There are different definitions available. In our work, we are restricted to use for now cavities which are built of spheres. So either the van der Waals surface or the solvent accessible surface, but we don't have support yet for something like the solvent excluded surface. And then the polarizability. The polarizability is an experimental quantity, so it's really nice because it already takes into account all the degrees of freedom of the solvent. It's a macroscopic quantity, so it's really convenient to use that. And then we can add on top ions, so we introduce screening effects. Here I'm reporting some comparison between the Coulomb kernel and the screened, the Yukawa kernel. So as you can see, really, whenever we add ions, everything becomes short range in some sense. I will present today 3 different models. The first one, the most simple one, is the Cosmo model. In this case, we say that in the outside we have the electric constant, which is infinite, as in a conductor, and so all our electrostatic problem is somehow restricted to the cavity. Inside the cavity, we have the potential of the solute, which is what it is, and then we have the reaction potential that we want to find. Once we find the reaction potential W, we can compute the solvation energy as this integral with the solute density here. And in this case, since the environment is a conductor, we know that the potential inside of a conductor is constant, and in this case, we set it to 0. And so the problem is a partial differential equation defined inside with boundary conditions at the cavity. And this localization of the problem is what makes DD Cosmo, for instance, really, really fast. Then we can relax a little bit the conditions. For instance, we allow for finite dielectric permittivity, and then we fall in the polarizable continuum model definition. Now the domain of the partial differential equation is the whole space. We have 0 conditions at infinity, and we have jump conditions because in a simple model, the dielectric constant instantly jump from the outside value to the inside value. So we have some jump conditions here. But once again, we can solve for the reaction potential, and once we have it, we can compute the energy. And finally, we can also add ions, some Poisson-Boltzmann ions to the solution. And we already saw this earlier. We have, again, the Poisson problem inside, and we have a screened Poisson problem outside, and those are coupled by the jump condition, basically. And we can, once again, find the reaction potential and then compute the energy. In general, the linearized Poisson-Boltzmann, or even nonlinear one, is the most general case. And then by setting to 0 the ion concentration, we recover the polarizable continuum model. And by setting the dielectric permittivity to infinity, we recover the Cosmo case. Or we can take even a shortcut by doing one of those 2 things to go directly to Cosmo. And another thing we are really interested in is having a very good computational cost scaling, because if we want to do biophysics with these kind of models, then we really need something which is linear scaling. This is an comparison between a traditional polarizable continuum model implementation and ddCosmo. And as you can see, for the largest system, the linear scaling implementation takes just 25 seconds versus the other one, which takes 8 hours. So really, if we want to go to biophysics, we need something which is linear scaling. And today I will present the library and also some general theory that we developed. It's really helpful to derive the working equations for this kind of models. And also I want to put a little bit of definitions here because I will use those definitions later on in the presentation. In general, we have a system with a solute density, which is fixed, is given by the problem. It can be charges, it can be multiples of higher order if we have like amoeba, like moving dipoles or quadruples, or it can even be a quantum mechanical density, it can be anything. And this solute density induces some density of charge in the environment. I will also consider the discretized model. So everything in this theoretical part is made of matrices, vectors. I'm not considering integral equation now and not even partial differential equation. I'm already considering the discretized version. And if we have a linear polarizable embedding model, it can be any linear polarizable embedding model, then we can write a linear system for the polarization density. Where we have some matrix which depends on the geometry of the system, our polarization density, or reaction field even. And on the right-hand side, we have some electrostatic property of the solute density. This electrostatic property, or in general, is a linear function of it. And then once we solve this, we have to compute some energy. And the energy can be, the expression can be seen from this picture. We will have some self-interaction of the solute density, which is this E of m. Then we have a bilinear interaction between the solute density and the solvent-induced density, which is this term here. And as you can see, this function may be the same, may be different, but it's again linear in the density of the solute. And finally, we have a self-interaction term of the solute density, which is this last one. Now, if the matrix is symmetric and positive definite, and the two functions psi and phi are the same, then we fall in the case of a variational model. Variational means that the polarization density x is the unique minimizer of the energy function. And this simplifies the analytical derivatives, because whenever we want to compute a derivative, we simply take the partial derivative, and we don't have to worry about terms coming from the chain rule, because this will be 0 because we solved our linear system. But often we have to deal with non-variational models. For instance, all our domain decomposition approaches are non-variational, or the induced dipoles of amoeba are non-variational. There are many cases in polarizable embedding models, and can be either because the matrix is non-symmetric, or the two functions are different, or even a combination of both. And in this case, the derivatives are difficult because we would need to compute this chain rule term. And especially this derivative of the solution with respect to some perturbation is really complicated to compute. And we don't want to do that. So we take another route. We define, instead of an energy expression, we define a Lagrangian functional, where through a set of Lagrange multiplier S, we enforce the solution of the linear system. Now, once you solve the linear system, those two expressions are actually the same. We recover the energy expression. And once we have defined the Lagrangian functional, by minimizing with respect to S, we get back the original linear system. By minimizing with respect to X, we get a new adjoint linear system, which is here. And the derivatives are easy again, because we don't have to worry anymore about chain rule terms. We can simply take the partial derivative. And so no derivatives of the solutions, which we don't want to compute. The price is that the computational cost is doubled. But if we want to do derivatives, it's way better to have a double computational cost rather than deriving for each perturbation. Like for gradients, the perturbation are all the nuclear positions. So this would be lots of terms. And as a self-consistency check, we can see that if the two functions are the same and the matrix A is positive definite, then we go back to the variational case that I showed earlier. And then this also allows for a nice strategy of computing the forces, which is somehow different with respect to what we saw this morning. basically what we do is we first discretize the problem, and we get a linear system. And then we differentiate the discrete Lagrangian, the one I showed before. And as you can see, for the gradients, for instance, we have a term from the multiples. Then we have the gradient of this function psi, which will be some derivative of a Coulomb kernel or something like this. Then we have the derivative of the matrix. This is difficult because it contains many contributions also from the change in the surface. And finally, we have also the derivative of the phi function, which will be similar to the other one. But this strategy has some advantages. First, the discretization does not matter. The forces always sum to 0 because the derivative is exact. Actually, we have an exact derivative of a approximate energy. And second, the fact that the derivatives are always exact derivatives makes possible energy conservation in molecular dynamic simulations. And also, by employing this approach, it's quite easy to get the forces per atom, provided one can build these three contributions. However, by now, we cannot really differentiate the forces into the electrostatic, the electric jump, and in the osmotic pressure. But maybe we can think about it. Maybe it's possible. I'm not yet sure. We never really investigate into this. And so with this general theory, I can now present the domain decomposition X library that we developed. This is a very long work. It took many years. It's a collaboration, as I said, between mathematicians like Benjamin Stamm, my current postdoc advisor, Alexandre, who coded most of the library, Abhinav, who coded linearized Poisson-Boltzmann, the forces of the linearized Poisson-Boltzmann method, and chemists like Filippo, Michael Herbst, and me. And the first model and the method that we implemented was the domain decomposition Cosmo in 2013. And then later on, we developed something for the polarizable continuum model. And then we started investigating the linearized Poisson-Boltzmann. Also, we coupled all our methods to quantum mechanical solute, which has some additional difficulties. And only recently, we decided to bundle everything inside the library. And we also say that we wanted to achieve this linear scaling regime. So the original implementation of the domain decomposition PCM was not linear scaling, as well the original implementation of the DLPB, because we have some electrostatic interactions, so it's n squared. But Alex coded a FMM solver within our library, which is specifically tailored to work with spherical harmonics. So now everything is really linear scaling, and we have forces for all our methods. And we also implemented a few interfaces to other codes to give some example now to couple our library to other codes. We coupled to a quantum mechanical solute in Psi4, it's a quantum chemistry package, and also to Tinker for classical solutes. Yep, everything is linear scaling in memory and time. The library itself is written in Fortran, but we also exposed APIs to C, C++, and to Python. It's open source, so if you want to contribute, feel free. And also, if you have some requests for functionalities, you can open a issue on GitHub, and at some point we will take care of it. The code is available here, and also you can download actually binaries from PyPy and Conda if you want to use it easily. Linear scaling is achieved through two main strategies. First is sparse formulations. So for instance, DD Cosmo is a sparse formulation because in our matrix we have non-zero terms only for spheres of the cavity which overlap. And so this is Karambin, I think, and this is some overlap matrix. As you can see, most of the matrix is 0. So doing a matrix vector product is linear scaling. Or we have our fast multiple library, which is in-house fast multiple library. It uses different tree. Instead of dividing the space in boxes, we use a recursive inertial bisection. So we find we cut in half by trying to minimize the momentum of inertia. And this gives more balanced trees, and we found out it works quite well for these cavities made of spheres. And also this library directly works with the spherical harmonics that we use also to discretize our differential and integral equations. And those are the fundamental steps of a calculation. want to spend some time on this because later on we will see this a few more times or in the actual examples. So first we have to compute the right-hand side, which is this phi, is basically the potential of the solutes. For the DLPB, we also have the normal derivative. We have also to compute the electric field of the solute. Then we need a joint right-hand side, is psi. This is basically a representation of the solute density in spherical harmonics, but for point multiples, it's analytical. I will go back on that later. Then we have to solve the linear system. We use an iterative method. We use a Jacobi method with acceleration. And once we have the x, the induced density, we can compute the energy as a scalar product. Then, if we want to do analytical derivatives, which can be either forces or Fock metrics, because we are doing a QM PCM calculation, then we need also to solve the adjoint linear system, this one here. And then we can, once we have x and s, we can assemble the derivatives we are interested in. But the specific formula depends on the derivatives we are actually interested in. And since the expression for phi and psi and for the forces are analytical for solutes which are made of point multiples, I thought about creating a module in our library which gives some functionality for arbitrary solutes made of arbitrary multiples, meaning we have an arbitrary high spherical harmonics order. We can have dipoles, quadrupoles, octupoles, and so on. But they must be in real spherical harmonics because it's what our library internally use. So if someone has Cartesian multiples, there's some conversion step to be performed first. And so given set of multiples in real spherical harmonics, we have functions to compute the electric potential, field, and field gradient using the fast multiple method acceleration, so linear scaling. Then it's very easy to compute this psi. It's natively linear scaling, so we don't have to worry about fast multiples here. And then we also have some functionality to easily compute forces terms. Again, with FMM, because also in the forces we have electrostatic interactions. So FMMs are needed. I did some benchmarks to show that our computational cost. I took some PDB files, and this is all run using Tinker DDX. So I create some Tinker inputs using the Amber 99 force field. This is just to benchmark. So this was the force field bundle with Tinker. So I took the easiest one. And using 10 CPUs. We have also parallel implementation using OpenMP for the main loops. And as you can see, again, those are all the steps. We have the right-hand side, which is costly, but not super costly. Then we have the adjoint right-hand side, which actually is for free, basically. It's milliseconds, even for the largest system, which is a virus. And then we have linear system, adjoint linear system, and force. And in all the cases, you will see that they have roughly one-third of the total computational cost. So for this biggest system, it takes us like 100 seconds or something. And then this is for the DPCM. We have something similar. This was probably badly conditioned, so we had a few iterations more, but still it's linear scaling, one-third, and right-hand side is cheaper. And the cost is a little bit higher. Here we have for the largest one, 1,000 seconds or something. And then the DLPB, the DLPB is even more costly because we have two equations. One for the outside, as we saw earlier, we have the screened Poisson outside, and then we have the Poisson inside, and those are coupled through complicated conditions, so it's more costly. But again, we see the same trend, even if it's more costly. And yep, and this was the adjoint right-hand side was too fast. I couldn't really measure the time. And then also I measured accuracy. Here we report the DD Cosmo and the DLPB, but also for the DPCM is the same trend, more or less. We observe exponential convergence of the error. Here I'm changing the maximum angular momentum of the spherical harmonics discretization that we use, and this is the error. And using Lmax equal to 5, we still have 1% error, and with Lmax equal to 10, we fall in the range of 1 per 1,000. And our convergence of the error is quite good. I also compared again APBS and TABI PB. For large errors, we are doing worse than the other codes. We are taking more time, and little bit less memory, but if we go to higher accuracies, then we are performing better in terms of both of memory and time. And this being said, I would like to present a couple of examples of coupling the DDX library either with Python, with Tinker, and with other things. And for the Python one, I have actually Jupyter notebook here. You should be able to see just to present a little bit how it works. First, we import this. This was installed through PyPy, so it's quite easy to install, but you will need a Fortran compiler because it has some compiled Fortran code inside. Then we define the input data, which is charges at the atom positions, van der Waals radii for all the atoms, and the centers of the atoms. Then we have to convert, as I said before, the charges to monopoles, and because we go from Cartesian multiples to spherical harmonics multiples, here is just simply a scaling by square root of 4 pi. And then we also convert all the distances to Bohr because our library uses atomic units, so we don't want angstrom inside. And then first we have to initialize the model. It's something, this takes care of all the constants, pre-computed constants and geometry related things. And here I'm using Cosmo. So initialize model. And then once the model is initialized, we also have access to all the fast multiple method things because the fast multiple method 3 was built. And so we can use tools for multiples to compute electrostatic properties. And the psi, this adjoint right-hand side. And then we go on and we have another main object, which we call state. A state is something related to a specific right-hand side, because for instance, in quantum chemistry calculation, sometimes we have the same geometry, but multiple densities. So we wanted the flexibility to keep everything that's geometry related the same and then change just the right-hand side. So I initialize the state by plugging in the model and the right-hand side. And then first I solve the linear system. And here I'm also exposing something for the guess, because we also had some discussion before. Sometimes we have to solve these problems for structures which are similar. And so we may have some better ways of providing the guess. So we are really allowing the user to specify the guess. We believe that this is something important that should be high level in our library. So we do some simple guess and then we solve the linear system. And once we have solved the linear system, we have access to the induced density. And so we can compute the energy as this scalar product here. And then if we want to do the forces, we have the 2 additional steps that we saw before. First, we have to compute to solve the adjoint linear system, which is this. And once we have also the adjoint linear system, we have to compute the forces. Forces are made, I split them into kind of contributions. One is everything that does not depend on the specific nature of the solute, because we want to be agnostic with respect to the kind of solute that we have. Someone may be interested in quantum mechanical solutes or in high order multiples or in point charges or something polarizable, I don't know. So I said, okay, first we have everything that does not depend on the nature of the solute, which is this first contribution, and then everything which depends on the solute. Well, if the solute is made of point dipoles, then we have the helper functions that I mentioned before. But if the solute is something strange, like quantum mechanical density, then the user should use this quantum mechanical package to actually compute some force terms. So yeah, this is it. I will go back to the other examples. And if you have any questions, feel free to interrupt me even before the end. And second, another example I want to provide is a little bit of coupling with a classical mechanic molecule that we did in Tinker. As I said, the right-hand side phi is analytical for multiples. Also, we can compute it for arbitrary multipolar distribution. And psi is this integral of the solute density with some radial part and some angular parts. But if the solute density is point multiples, it's analytical, so it can be done with DDX. And so we coded this Tinker interface using directly the Fortran routines of our code, as Tinker is written in Fortran. And by now we have available energy, geometry minimization, and also molecular dynamics for Cosmo, PCM, and linearized Poisson-Boltzmann. And to test it up, yesterday I launched some molecular dynamic simulations using a couple of systems, one of 170 atoms and the other one roughly 1000 atoms. And I run simulations in vacuum with DD Cosmo, DD PCM, and DD LPB. And first I run 2 picoseconds in the NVT ensemble, and then I run 2 picoseconds in the NV ensemble just to see if we are conserving the energy. As you can see, the DD LPB one is not yet finished because I launched this yesterday. But still, and then I wanted to see how it performs this constant energy part, and this is some close up. And we have the vacuum in black, and again our 3 models colored. I'm quite satisfied because the small instantaneous fluctuations are quite small, and we have some drift, but also the vacuum case has some drift. Our is slightly larger, but we are doing something which is much more complicated than the simple vacuum calculation. And also I use a very loose convergence to do this simulation. I use 10 to the -4 on the residual of the linear system. So I think putting something tighter really improves the energy convergence, and also maybe using a higher Lmax may improve something. I also computed timings along the trajectory. So this is some average over all the frames, both the NVT and NV ones. As you can see, the initialization is for free. Also the adjoint right-hand side. And I don't think, no, yes, the right-hand side can be noticed, but still quite cheap. The joint right-hand side is for free, basically. And then here I have the 3 linear system, adjoint linear system, and force. And as you can see, yep, the LPB is quite more complicated than the other 2, but still we are doing quite nicely, and we can actually perform molecular dynamic simulations using continuous solvation models, which is something nice and quite new in some sense. And then in a different case, we also wanted to see how far we can push the limits of our implementation. And we had an idea to push it even further. The cavity is not really a physical quantity. It has 2 constraints. However, first, it must support the charge density. It's not allowed to have solute density of charge outside the cavity. And second, in our case, it must be made of spheres. And our computational cost is linear scaling in the number of spheres, not in the number of atoms. So our idea was, can we somehow reduce the number of spheres? And a very simple idea was to use a united atoms cavity. So we put larger spheres on the heavy atoms, and we remove the spheres on the hydrogen. And what also we did was, instead of keeping the hydrogen charge in place, we decided to use a tool from FMM, the multipolar to multipolar translation, to actually push the charges from the hydrogen to the heavy atoms. This does not really change the accuracy. We did some tests about it, but makes quite more simple the coarse graining process, because we can handle entirely the coarse graining in Tinker. And our library does not even have to know that a coarse graining is taking place, because the input will still be made of spheres and multipolar distribution. So we found quite nice to push the charges. And so we decided to try this. So what we observed is, for any given biological system, we roughly cut by 1/2 the number of spheres. And this is the time we also went to very large systems, like the viruses we've seen before. We went up to 7 million atoms with this biggest virus. And we compare the computational cost of a fine-grained DD Cosmo calculation with a coarse-grained DD Cosmo calculation. And as you can see, for the biggest one, we couldn't even finish the fine-grained calculation because it was asking for too much memory. We also investigated the energies, and we found out that the coarse-grained energies are systematically higher, but the relative energy differences, which are what we care about in the end, are quite robust with respect to this coarse graining. The time is roughly 50% of the fine grain one, or 25% of the fine grain one, and the memory is between same, or it can even go as low as 1/3 of the fine grain one. The other idea that we had and we implemented was to couple a polarizable solute with our polarizable embedding model. This is more complicated because now we have some fixed density of charge multiples of the solute. We have our solvent-induced density, and then we have the solute-induced density as well. So we have to achieve mutual polarization between all the components of our system. We implemented this within a quantum mechanical amoeba DD-Cosmo implementation. This was done in Gaussian in a closed source quantum chemistry package, but we have all the theory working. So at some point, one day we may implement this in Tinker as well, because we just have to remove the QM. So we simplify whatever we did. And everything is linear scaling because we can deal all this electrostatic interaction again using the fast multiple method. And the theory here becomes a little bit more involved. So I want to show you how we use our general theory to couple multiple polarizable embedding model. We have to distinguish if the two models are both variational, if one is variational and one is not, or if both are non-variational. This was the case of amoeba and DD-Cosmo, which are both non-variational. So the idea is we start by building either an energy functional or a Lagrangian if we have non-variational things in the middle. And we have some energy contribution from one model, some energy contribution from the other model, plus a coupling condition, which is in this case simply a interaction between charge densities. If the second model is non-variational, then we have to add a constraint to keep the linear system solved in the second model. And if both of them are non-variational, then we have a constraint on the first, more complicated coupling condition. And then the second model is replicated twice because it's coupled both with the x degree of freedom of the first model and with the y degree of degrees of freedom of the with the x degrees of freedom of the first model. So in this case, we have 6 sets of degrees of freedom. It's quite complicated. But the power is that once we have built this Lagrangian, then we can stop thinking. More or less, the idea is we combine 2 models, take some effort to write down a Lagrangian, but once we have that, we have just to do derivatives. We want our linear system, we minimize with respect to all our degrees of freedom, and we get a big linear system for the coupled case. Then we want to compute the energy, then we simply evaluate this Lagrangian once the linear systems are solved, and this usually gets simpler. And then if we want derivatives, we don't have to worry about derivatives of the degrees of freedom because the chain rule terms are all cancelled out. And so we can easily derive Fock metrics or gradients or even things to compute excited states in quantum chemistry. And still, if we want to also to couple with a quantum mechanical solute, everything is a little bit more complicated. The potential is still easy because it's a quite standard property, and every given quantum mechanical package can compute the potential of a density of charge. The psi is a little bit more complicated because here the density is not anymore made of point dipoles, point multiples, so we don't get some simplification in this integral. We have to do it for real, which is not nice, but still many code actually implement DFT, and DFT used as already non-analytical integrals within it, and they use this Becky quadrature, so we can simply rewrite this integral as a quadrature of these Becky points, and we can again evaluate our adjoint right-hand side. And we implemented this in Psi4, and by now we have ground state, either R3 Fock or DFT, and also we have excited states in TD DFT or TDR3 Fock formulation, or even this ADC2 method. Also, whenever we want to do self-consistent fields, in some sense, the density of the solute is polarizable as well. So we have to achieve mutual polarization between our polarizable environment and the solute density. So again, we write Lagrangian. Here we have the energy of the quantum mechanical part. And on top of that, we sum our Lagrangian of the embedding model. And then we have to minimize with respect to all the degrees of freedom. We get R3 Fock equations on top, and then we get our polarizable embedding model equations here. And also the Fock matrix contains some additional contribution due to our solute. But once everything is solved, we really have achieved this mutual polarization between all the parts. And then at the end, I put some mathematical details for someone who may be interested in how we deal with this domain decomposition formulation. It's a little bit technical. So we have mainly 4 tools. The first one is the Schwarz domain decomposition. Whenever we have a partial differential equation, which is quite simple and well known in the mathematical literature, like the Poisson equation or even the spin Poisson. There are analytical solutions out there, but the problem is that we are always dealing with very complicated domains because our shapes are quite irregular. We have this overlap of spheres and strange shapes coming from the geometry of the molecule. So the Schwarz domain decomposition idea is that instead of looking for a solution on the whole domain, we split our domain in overlapping patches, and then we look for a solution on the individual patches, which is much simpler because now the domain has some regular shape like a sphere, and we can use spherical harmonics to find some harmonics functions inside the sphere. But we have to make sure that on the outer boundary, we are enforcing the original boundary conditions. And whenever we are buried inside another sphere, we have to make sure that our solution on this sphere is consistent with the other neighboring solutions. But as you can see, this is really sparse because every local problem, is only coupled with the neighboring ones. And this is the trick that decomposition uses to achieve the linear scaling regime. Then we also use a lot of potential theory. So whenever we have some partial differential equation, we may want to go to an integral representation. And we do it for any given partial differential equation by using all the various single layer, double layer operators with Coulomb kernel, with Yukawa kernel, depending a little bit on the method we are using. And then we also wanted to localize the integral operators following some philosophy similar to the Schwarz domain decomposition. But now it's different because we are dealing with an integral equation which is defined only on the outside. So our idea was, first, we have to extend the domain because we want some as regular as possible domain. So we, instead of taking this boundary of the union of the spheres, we take the boundary of each sphere. So we have to add some new parts to the domain in the buried regions. But then we have to make sure, okay, this is a little bit technical, but yet we have to make sure that we are not doing anything wrong in this section. So we use some characteristic functions which make sure that our equation here is 0 equal to 0. And so those are these chi and chi j. And then once we take into account all these operations, then we can write our original integral operator S, for instance, as a sum of sphere to sphere contributions. Like we will have something, the diagonal sphere with itself, and then we have all the sphere-sphere interactions, and this creates some nice block structure, which can be, which is similar to whatever we get from the Schwarz domain decomposition. And our last ingredients are spherical harmonics. Since everything then is discretized on spheres, either on the inside or on the surface of spheres, then we expand all our quantities as a linear combination of spherical harmonics. And as an example, here I will report what we do for decomposition. For decomposition, we start from the Poisson problem. We use the Schwarz domain decomposition, so we get a collection of coupled partial differential equations. Then we use the integral potential theory to convert these local PDEs to local integral equations. And finally, we discretize everything using spherical harmonics. So in the end, we get a linear system. And as another example, I reported the DPCM. Now we have, again, partial differential equation with jump condition. So what we do here, we convert it to a global integral equation. This is the integral equation formalism equation. And then this can be split in two steps. One which is a new step, novel step, and the other one which is, again, a Cosmo-like step. So for this, we can use the decosmo, and this requires something new. And since this is an integral equation, we decide to use this localization of integral operators. And again, we get a system of coupled integral equations, and then we discretize using spherical harmonics. And so we get two linear systems in the end. I didn't report the DLPB, it's a little bit more technical, but if you want, just ask me questions about it. And as a summary, this is the final result of a very long journey. It took many, many years, different people working on this, chemists, mathematicians, and so on. By now, we have efficient and robust implementation for these three models. Everything is linear scaling in time and in memory. We have the forces and analytical derivatives for the three models. We also have developed this general theory, which makes it easy to couple with other solutes or to couple with polarizable things or in general. And we published this open source library. And so that if other people want to try it out, they can do it easily. And we have also many more things to do. We would like to couple this library to more packages, for instance, Chromax or other classical mechanics packages. We still have a lot of space to optimize. For now, we have simply put a very basic OpenMP parallelization, which is not even done that well. We still have some points where we can improve it so far. And we can also port this code to GPU. That would be possible, but it was never done. We could also go beyond electrostatic. There are many people working on additional terms to the solvation energy, like cavitation or dispersion repulsion. So we could collaborate with them to include in our library also these other things to make it easy to actually include these terms in a calculation. Yep, we also want to tackle the fully polarizable case in Tinker, and the coarse grain was really a pilot trial. We didn't investigate it that much. I think we can go to even more aggressive strategies like putting one sphere per residue, and then we didn't implement the forces for the coarse grain because it was a little bit technical and boring work, but it's possible. So we can also try to do that. So it's possible to do molecular dynamic simulation within this coarse grain scheme. And we also had some pilot implementation of the SCS surface and of the nonlinear Poisson-Boltzmann, but those are still pilot implementations, so probably it will take a lot of work to put them in the production library. So this was all. Thanks for the attention.
Thank you. Any questions?
How can you, are you for the SES surface? Can you still represent it with spheres? And so
it's a work from Benjamin Stamm and Chayuk Wan from 2018, I think. They defined 3 different objects that appear in a SES cavity. It's an analytical representation of the Connolly surface, and they have either parts of a sphere, and then they have something toroidal, I think, and then they have even something else, but I'm not really familiar with this. They implemented the code in MATLAB just for the energy, but it would be possible in principle to port it to more efficient language and then to also implement forces if needed.
thank you. Maybe this is a very naive question, but the ions that you put in the model, do they include solvation, or is a model for that, or you count on the solvent to actually behave and give that solvation effects that you mean? Some ions are really very strongly bound waters, and that might be important to.
We are simply solving the linearized Poisson-Boltzmann equation, so we get what the theory, Poisson-Boltzmann theory, gives us. So we, yeah, okay. But we could
because there are some exotic effects of water around certain ion. I mean,
but in that
are
case,
they included, or they should be just the result of the Poisson-Boltzmann?
For now, we have just a result of the Poisson-Boltzmann. But if one wants to go beyond this, they can put some explicit ions in the molecular dynamic simulation or in the structure, and then on top of that put Poisson-Boltzmann model. I think the best way to really include anisotropic effects like coordinations, or it would be either to include them explicitly or to go to something more fancy like 3D realism or something beyond.
So how is the GB versus PB molecular dynamics? So now that you have this in amber, so how does it compare with the more general use generalized Born in terms of energies and in terms of timing?
I think the generalized Born is simpler because it's some local effect in the this kind of models. Each atom is independent. We don't have this mutual polarization between all the components of the system. So of course it's much simpler, but it's also more approximate, because by including this mutual polarization, we include this n-body polarization effects. To be honest, these molecular dynamic simulations are like a result from a couple of days ago, so I don't have yet comparisons with other things. It's for sure it's more accurate, but still, all these kind of models, they all include some big approximation, because anyway, treating solvent as a continuum includes big approximation. So sometimes it may even be that a generalized Born by some error cancellation is more accurate, but yet I don't know for sure.
I mean, we don't do molecular dynamics, but we do we'll compare explicit and implicit water models and look at the protonation states. And they're actually, the implicit water model actually does a surprisingly good job on pKs. So, you know, there are times when it doesn't work, but it really generally works ridiculously well. So it's doing
Probably we don't know even why.
because it's implicit versus explicit motions. It's, you know, electric constant is real physics.
Yes, that's true. That's real physics.
You know, is it an average motion or is it a specific motion? You capture the average very, you know, immediately. You don't have to equilibrate over nanoseconds.
Absolutely.
So your sampling is much better.
Yeah.